Hey everybody, it's Mr. N, and this is the 11.3 Big Ideas lesson. This is on the areas of polygons. So let's first start off with this polygon, and we're going to talk about some parts and terminology that we have. So we're looking at this polygon, and just like in a circle, this central angle right here goes to the vertex, the center of this polygon, which you can consider the center of it. So it goes from a vertex here, vertex there, and that will form a central angle. And then if you take this piece, just like it is on this side, from that center to the vertex, that is what we're going to call the radius of our polygon. And then if you drop it down like this to be perpendicular, this is the radius. This would be something called the apothem. So that's what the apothem is. It's perpendicular from the center to the opposite side. So different word, apothem. I've always thought it would be a great name for a dog, but let's take a look at what the apothem can tell us. We can find the area of a regular polygon by using this formula. The area equals 1/2 times the perimeter. P stands for the perimeter, so we add up all the way around, and A is this apothem length. Now, here's how we can get this formula. If I take one of these triangles, so I'm going to say this where the central angle is formed, and I'm going to put it right here. I'll just use this one like this. So here's my apothem. This S stands for this side length right here. Now, the catch is, for this formula to work, you have to have a regular polygon. If it's not a regular polygon, it won't work. Now remember what regular means. Regular means all the sides and all the angles are congruent. So as long as it's a regular polygon, all these sides will be the same, and we can say that it's the area of one of the triangles times how many triangles I can make. So for example, in this particular situation, I would have one triangle, two triangles. I could break it up, and since this is an octagon, I end up with 1, 2, 3, 4, 5, 6, 7, 8 triangles that I've formed out of that. So I end up with the area of one triangle, which we could say is 1/2 times the base times the height. So that's 1/2 A times S, or 1/2 S times A, the way they wrote it here. And then if I just get rid of these parentheses, you can use commutative property. What you will notice is the number of sides times how the length of that side is going to be your perimeter. So if this was, say, 5, and I had 10 of these, then the perimeter would be 50, right? So the number of sides times the length of the side is that perimeter. That's where we get this. And this A, which was the height, is the apothem. So that's where this formula comes from. And that works again for regular polygons. So let's move on. And if we've got a kite, the next thing we're going to talk about today is we can find the area of a kite, and the area of a kite will be 1/2 this diagonal times 1/2 that diagonal, because again, you can break it up into these triangles that you can form and find each of them. So that's what it would look like if the kite was shifted over a little bit. So it's 1/2, 1/2. But then I've got the top part and the bottom part. The 1/2 came from this length, the 1/2 came from that length of the other one. So that's where I got this 1/4, but then I have the top and the bottom. So the formula for the area of a rhombus or kite is 1/2, because I multiplied this answer by 2, times the product of the diagonals. So this may seem a little confusing with all these 1/2s and 1/4s. So, but that's how it's developed. But just as long as you remember that the area is going to be 1/2 times the product of the two diagonals. So here's diagonal 1, there's diagonal 2, there's 2, there's 1 in this drawing. Area will be 1/2 the product of the diagonals. and that's on a rhombus or a kite. All right, so let's turn to page 327 in the student journal, and let's do some of these problems. All right, so for the first problem here, we have to find the area of this kite, or actually this one is a rhombus. So let's do this. And we know that the area, from what we just talked about, is 1/2 the product of the diagonals. So the area is going to be 1/2. Well, this diagonal is 14. And then we are given that this piece is 10 and that piece is 10. I'm assuming that they're pointing to that. So the other diagonal is 20. So the area will be 1/2 of 14 times 20, so you could think of it as 7 times 20, so 140 square inches. Now, suppose though this piece was 10 here, and this piece was 7 there. Well, you could find this diagonal by using the Pythagorean theorem, because remember, on a kite or a rhombus, these will be perpendicular. All right, so let's move on to the next problem. Over here, I'm going to assume that that's the 2 they're talking about. It looks like it's much longer than this piece. So this diagonal is 4. And then this diagonal would be 8. And so on the kite, the area is 1/2 the product of the diagonals. So the area would be 2 times 8, which is 16 square centimeters. Again, if they had given you this piece instead, you'd have to use the Pythagorean theorem to get that diagonal. All right, let's move on to the next problem. It says the measure of the central angle of a polygon with 8 sides. So the way we could do this is, you got to remember, whatever, since this is a regular polygon, whatever I do here, I'm just drawing part of a polygon, and I have this is my central angle. Remember, all these central angles will add up to be 360. And if it's got 8 sides, that means there's going to be 8 of these angles. So 360 divided by the 8 is going to be the central angle. So this comes out to be, the central angle is going to be 45 degrees on this one. All right, next problem. It says the central angles of a regular polygon are 40. How many sides does the polygon have? So it's similar to this. If this central angle is 40 degrees, and I know that all the way around is 360, this time we'll say 360 divided by the 40 is going to be the number of sides. And that comes out to be 9. All right. Moving right along, let's see what we got next. It says, a regular pentagon has a radius of 4 inches and a side length of 3 inches. So it's a regular pentagon. And we can sketch it on the side here. We'll sketch a small regular pentagon. It's good enough. It's not so regular, but you get the idea. Okay, and it has a radius, that would be the radius, of 4 inches, and a side length of 3 inches. We have to find the apothem, which would be that right there. So this would be 1.5 if the side length is 3 and then the radius is 4, and I could find the apothem right there. Because I could say that the apothem squared, here, let's put it over here since I've got a little bit more room. I will erase this. And I have the apothem squared plus 1.5 squared equals 4 squared. So A would be the square root of 16 minus 1.5 squared. And I'll quickly put this into my calculator, and this comes out to be 13.75, which gives me an apothem of 3.71. All right, so now we've got to find the area of this pentagon. So we know that the area is going to be 1/2 times the perimeter times the apothem. So that's 1/2, and the perimeter, if this is 3, the side length is 3, and I've got 5 sides because it's a pentagon. This would be 3 times the 5 times my apothem, which we just found as 3.71. So let's multiply all this out on the calculator. And that would give me 27.825. And this was inches, and these would be square inches. All right, let's move on to number 6. On number 6, it says, find the area of a regular hexagon that has an apothem of 10 units. So a regular hexagon, we'll quickly sketch out what we're looking at here. And 1, 2, 3, 4, 5, 6. It's as regular as I can make it. This one doesn't have the fancy shape tools as my other software, but we'll say that that's the center right there. And this is the apothem, which is 10, and that'll be perpendicular like that. And then we need the radius, which I'll put here in red. That will be the radius, and the length of one of the sides. So this is the radius, and I need the length of one of these sides right there. Well, here's what you got to understand about a hexagon. And a hexagon is one of those tricky ones because it has something special going on. On a hexagon, there's 6 sides. And remember how the other problem we said, okay, 360 all the way around. So if I make these triangles in here, so if I make this triangle, this angle in here will be 60 degrees. These angles down here will be 60 degrees because that's R. And on a hexagon, what ends up happening is you form these equilateral triangles on a regular hexagon. So I'm going to pull this out. I'm going to put this triangle right here. This is my apothem. This was my side length. This is the radius. I knew the apothem was 10. So I end up with a 60, 30, 90 triangle. So if this is 10, then this piece right here will be 10 divided by the square root of 3. So the whole side length will be 2 times that, so that'll be 20 over the square root of 3. And even the radius will be 20 over the square root of 3 because I would double this length right in here. So, but again, we said that on a regular hexagon, this is a special one, you will get a triangle when you make these triangles out of it like this that are all equilateral. Only on a regular hexagon. It doesn't work on any other ones, just on a regular hexagon. So that would be the radius, this would be the side length, and these two would be equal because it's an equilateral triangle. So over here, the radius comes out to be 20 over the square root of 3, and a side length is also going to be 20 over the square root of 3. You can rationalize the denominator by multiplying the top and bottom by square root 3. So you could say that it's 20 root 3 over 3 for each of these. All right, now we have to find the area. So to find the area, we have 1/2 times the perimeter times the apothem. We know that the perimeter of this, we know that the side length is going to be 20 over root 3, and I have 6 of those, and then I was told the apothem was 10. So let's work all this out. I end up, this reduces out to be 10, so I'll get 60 over root 3 times my 10, so this will be 600 divided by the square root 3. If you wanted to rationalize it, you can. If you wanted to present this as a decimal, I'll even let you. It just depends on the problem if it asks you to keep it as a decimal or in square root form. As a decimal, this would be 346.41, and these would be square units. All right. So hopefully this wasn't too bad. Some of these on finding the apothems are going to be a little tricky. Just remember, though, you can make those triangles out of it and think of it that way. So hopefully the homework won't be too bad. So thanks for watching. Hit that like and subscribe button, and I'll see you in the next video.